Hello, this is the presentation for the Quantile formulation for optimization under a qualitative risk constraint, and it is presented in Cancun, Mexico, the 7th of December, 2022. The motivation for this presentation is probability constraints. Probability or chance constraints are used to model qualitative risk. This is fatal failure or death. For example, if you die because you ate a bad cheese or something like that, it doesn't really matter how much you ate beyond what is fatal. It basically just matters that you ate more than what was safe, and so you die. So this is the idea of qualitative risk constraints, that we have a criterion for a failure, and it's basically binary. Either the system fails or the system doesn't fail, and that's what we call the probability constraints. These are used in telecommunication networks to limit loss of information, error rates, and other measures of performance. It's used also for power control in chemical plants, financial investments as well, to limit risk of ruin. It's used also in the service industry to comply with regulatory quality of service requirements. In this particular presentation, we are going to be talking about examples where failure of medical devices, such as robot arms for assisted surgery, can lead to fatal outcomes. So basically, the chances of leaving safety regions should not exceed a given probability. The distribution of formulation goes as follows. We have a control variable, theta, which is in d dimensions, vector in d dimensions. We have a nonlinear cost function, j of theta, which is usually in the form of an expectation of some kind of instantaneous cost function. Xi is, in this case, a random vector with distribution that is independent of theta. The safety region is defined through the random function g of theta and xi. So this safety region is the one that I'm annotating here. So that would be the safety region is the one that tells us that this random function g of theta has to be smaller or equal to alpha, and we want to stay there. That is the safety region. For example, in chemical plants, they want temperature, pressure to be within some limits, because if it exceeds that, for example, the tank where the various chemicals are being processed could actually blow up, could get fire or something like that. And in our case, we will see several examples of how we want to keep, why we want to keep in the safety region. Sorry. So the problem is basically the following. In the distributional formulation is the following. We say that the constrained function b of theta is defined as p minus the probability of keeping in the safety region. So this way, the problem can be reformulated as minimizing j of theta subject to b of theta less or equal to 0. This is the traditional formulation that appears in all the textbooks of nonlinear programming, and that's the one that we're going to refer to. But we call this the distributional formulation because, of course, this quantity that appears here, the probability that this function g is less or equal than alpha, corresponds in reality to a cumulative distribution function. So that's why we call it the distributional approach. To solve nonlinear gradient-based, optimization, to solve these problems, there are many methods. We can use projection methods, penalty methods, Lagrange duality methods, many different methods for solving the problem that is boxed in this in this slide. So in particular, we're going to be using one called the Arrow-Hurwitz algorithm, which is a Lagrange duality method and is based on what many of you will know as the Lagrange duality, the saddle point method. In this algorithm, we include Lagrangian. So we formulate the Lagrangian, including what we call the Lagrange multipliers, lambda. And we look at not just the control variable theta, but we also look at the multiplier lambda. And so we increase the dimension of the state space, well, or the control variable, and we use a recursive algorithm that is gradient based, because here the J prime and the B prime refer to the corresponding derivatives. This is the algorithm in one dimension, but of course this algorithm can be used in several dimensions, and that would be replaced by the gradient. There are several results that I'm going to cite without giving you exactly where they are. They're very well known for a long time, and they appear in most of the books on optimization. One of them tells us that if we have this sort of equation, which is xn plus 1 equals xn plus a little change, so there is incremental equations, we call these iterative or recursive algorithms. Then from the sequence of values of the iteration, we define a continuous time function by doing the interpolation. In this case, I just defined the constant, piecewise constant interpolation, but you could use linear interpolations as well. And so that we turn a sequence of points into a sequence of functions. And in functional state space, we can prove that as epsilon tends to 0, the algorithm converges in the subnorm to the solution of the ordinary differential equation dx dt equals v of xt. So because of this result, now we're going to associate this what we call the vector field to what is driving the what is basically driving the algorithm, the Hurwitz algorithm, and that will be the vector field corresponding to the AAH algorithm. The second result is that if the problem is a convex nonlinear problem, then, well, the real parts of the gradient of the vector field are all non-positive, and that actually implies stability of the ODE, a unique asymptotically stable point, and that asymptotically stable point is actually the optimal point that solves the constraint optimization problem. We're going to be using these results later on. They're just basically background results. So in our example 1, there's a robot laser on a linear rail pointed at a location theta bigger or equal to 0. It causes ablation that can reach up to theta plus minus basically a noise, and this noise is uniformly distributed in some region. So the aim would be a target, which I call bar theta, which is basically for this example, it's just located at the origin to simplify things, but at a distance d of the target, there is a delicate tissue that should not be subjected to ablation. So the whole idea is that in this linear rail, we want to control the position so that it gets as far as possible to the target without, if possible, of course, without actually getting into this delicate tissue, without touching it. So the safety region is what we defined as, theta minus xi bigger or equal to d. So changing a little bit the terminology, this can fit exactly our formulation, which is minimizing j of theta. In this case, is very simple, subject to the probability that xi minus theta less or equal to alpha be bigger or equal to p. So we want to keep in the safety region. This is the vector field that defines the drift of the Arrow-Hurwitz algorithm in this particular example. So I put in the left the vector field, and this is the picture of the vector field. Now, I like this visualization because you think about, for example, the flow in a pond or a fluid, and you think about the particles that would be moving. Well, this describes how the algorithms actually move. So it's a way to analyze algorithms, to do algorithmic analysis, which is a little slightly different from the regular ways that most people analyze algorithms. And in this particular case, we can, just looking at the vector field, we can see that it is apparent that no matter where we start the algorithm, it will all whirl around the optimal value, and it will tend to the optimal value of theta star and lambda star in this case. Well, that's what we see, but I've got a little surprise for you because it's not really this way. The pathology, we're going to now talk about the pathologies of the distributional formulation. The first pathology will be non-convexity. We all know that constrained nonlinear programs require convexity to ensure convergence to the optimum. It's very hard to deal with non-convex functions. Now, distribution functions, as I show here, are neither convex nor concave. To the left is the actual distribution function for example 1, the one that I just showed you. On the right-hand side, we show the distribution, the actual, this is the constraint function for a beta distributed random variable. So what I'm showing here is the constraint, the function b of theta as a function of the different values of theta. So on the x-axis is theta, and on the y-axis is the constraint function b of theta. Clearly, these functions are, well, they're convex, for example, in this region, but in this other region here, it is not a convex function. So same thing with the linear case. So that's a problem in general that has been identified for decades for this type of problems. If we zoom out on the vector field, then what I showed you before was this tiny little part here, and it all looked really honky-dory. Everything was fine. We thought that regardless of the initial values, that we were going to always converge to the optimal solution. But when we zoom out and we actually look at the whole vector field, we realize that this is not the case. If we initialize our value of theta and lambda in any region that is, to the left of, this is 0.95. So for any theta 0 that is, less than 0.95, the algorithm arrows go up and to the left. So on the theta dimension, they're trying to reach the unconstrained optimum. And on the multiplier dimension, they're actually going to infinity. So these algorithms might look like they were working fine, but if one actually takes a look at the whole picture, this is a pathology. Now we're going to talk about what we call the vanishing gradient pathology. As I mentioned, the non-convexity pathology has been described before. As far as we know, the vanishing gradient pathology has never been described before. So I hope that this will be clear enough. Convexification methods like the augmented Lagrangian, like the Arrow-Hurwitz beta method and other methods will not work in this case of the example 1 that I showed you, either for Arrow-Hurwitz algorithms or penalty methods. You can see the paper for all the details because we actually prove that they do not work. What is our hypothesis? Our hypothesis, based on the visual that I just showed you on the vector field, is that the main problem is the bounded support of the distribution functions. The non-convexity of the constraint function is, of course, a consequence of this as well, but it's more harming to the algorithm, the fact that there is a bounded support, and I will show you why. So, For this pathology, the vanishing gradient, we're going to consider the problem as usual, and which are the assumptions. For each theta, G is monotone increasing on the second component on Xi, and so there is a generalized inverse, and this inverse function exists, was well defined. We're going to assume that G is continuously differentiable in theta, and that Xi is a continuous random variable with bounded support. So we start with the bounded support, left and right, L and R. The undesirable region, well, I call it the undesirable region, is defined as the values of theta such that this inverse, this is basically the quantile, is less or equal than the left value. The interpretation of this region is that for all theta in that region, in order to be in the safety region where G is less or equal than alpha, it means that we are on an area of the random variable Xi where the distribution is equal to 0. That's basically why I call it the undesirable region. Now, let theta bar be the minimum of J of theta, which is the unconstrained optimum, and we will assume that theta bar is in the undesired region, which is the most common assumption in these cases, because otherwise we wouldn't need the constraint. Under these conditions, we prove in the paper that the Arrow-Hurwitz algorithm diverges when initializing in the undesired region. Specifically, theta n converges to the unconstrained optimum, and lambda n converges to infinity, just as we saw in the visual. But this is a general result. Secondly, the penalty method algorithm converges also to the unconstrained optimal value. I haven't seen, I haven't really worked out the projection methods and other methods, but I think that they also suffer from this vanishing gradient. The interpretation of that is the following. When the control variable falls in a region where this was the safety region, implies that theta has to be in U, then the corresponding value of this random variable is outside the support of the distribution. So basically, this value, we would say, it's impossible. That's basically what it means. But the algorithm doesn't know that. And so the machine, your computer, will keep using these values. At these moments, the distributions, the distribution functions are either 0 or 1 at those points. And from the differentiability assumptions, it follows that the derivative of the constraint function b at all those points is going to be 0. In other words, the algorithm doesn't even see the constraint in these cases when it falls in the undesirable regions. And well, I can tell you for experience that algorithms do fall there sometimes. So it's good to know that this is the problem. Now, this the theorem and the motivation example 1 was done with bounded support, but because for any distribution, the gradient of the distribution function converges to 0 when either x goes to minus infinity or x goes to plus infinity. That's by definition. So it follows that numerically, for our computer, all distributions have bounded support, because beyond certain points, the computer takes those, truncates those very small values, it truncates them to 0. So that's why we call it the pathology of the vanishing gradient, because in numerical jargon, this would be vanishing gradient. So what do we do to solve the problem? To solve the problem, we propose a quantile approach, the quantile formulation of the problem. The quantile function, I just do a reminder here, the quantile function is defined by the generalized inverse function of a distribution function. And I might remind you that in our model, the random variable Xi has a distribution which is independent of theta. So this quantile of the distribution is also independent of theta. So our theorem is the following. Assuming that the function G, which is the one that defines the safety region, is monotone non-decreasing in C for every value of theta. And so we can define the inverse function. Then the following statements are equivalent. We're going to recognize here the probability constraint in the same way that we had it in the distribution formulation. This is basically the equivalence, just using directly the definition of the quantile and reworking what this function H means in terms of the function G. We can reformulate that later on in terms of the function G directly, evaluated now at the quantile. So while the original formulation evaluates the function G at a random number, at a random value, in the quantile formulation, the function G is evaluated at a constant value, which is the quantile, that particular quantile of the distribution. So the quantile formulation tells us that we want to minimize J of theta subject to G of theta evaluated at the quantile less or equal than alpha. The two formulations are equivalent under these assumptions. Now, if instead of monotone non-decreasing, the function was non-increasing, then instead of using the quantile P, we use the quantile at 1 minus P. And you can take a look at the paper to see why this happens. Okay, so what are the properties of the quantile formulation now? The properties of the quantile formulation. If J of theta is convex, which is a very common assumption in nonlinear optimization, we also assume that for an infix Q, the function G, which is the one that defines the safety region, is convex in theta. And we assume that C has a distribution which is independent of theta with quantile function Q. And we assume that the function G is monotone in C and it has this inverse. So now we redefine, I call it B tilde. We redefine the constraint, and the quantile formulation is now a convex nonlinear problem. So we've turned into a formulation where the constraint was neither convex nor concave to a formulation that is equivalent, but where now the constraint is ensured to be convex. For those reasons, the Arrow-Hurwitz algorithm and other gradient-based methods algorithms will actually now converge to the optimal solution. There's no pathology. The remark that I want to make follows some of the referee's remarks. Thank you for pointing that out. Now, even assuming that G is convex, which we do here, we assume that G is convex. In the distributional formulation, that leads to a constrained formulation where the constraint B of theta is not convex. Whereas in here, even assuming G is convex, the quantile formulation gives us a constraint which is convex. So the convexity problem or pathology that I was talking about refers to the convexity or non-convexity of the constraint function B of theta or tilde B of theta, not the convexity of G, which is basically the one that defines the safety region. Well, back to example 1. What happens when we do the transformation? When we do the transformation, and it doesn't matter how much you zoom out, it looks just like that all the time. It's very, very smooth, and it definitely does converge to that optimal solution. So this is, the typical vector field for Arrow-Hurwitz algorithm when we have a convex problem. Now we go on to a different, an extension. What happens if we don't have just one random variable, but we have several random variables? So these examples are going to show you how we can manipulate multivariate problems and still use the same formulation and theorems that we developed in the first part. So suppose that you're manufacturing a robotic surgical arm. The vibration of the cutting tip at the end of the arm is a concern. So for regulations, they require to bound the probability of exceeding a certain distance from the center of the probe along each of the principal axes. So what do? Here, the planar position of the arm is a two-dimensional normal random variable. We have, in this particular case for the probe, that the variances are scalable. That's why we call it elliptical regions. While they can be correlated, there is sigma is the variance covariance matrix. It turns out that the variance of the C2, the second position, is proportional to the variance of C1. We use the Mahalanobis distance that it says, we use the fact that the Mahalanobis distance delta squared, which is defined here, has a chi-square distribution. So this distance takes multivariate normal random variables and defines a single random variable, univariate. So that's the way that we're going to manipulate the problem formulation. So the problem formulation, the original one, is minimizing J of sigma, subject to the probability that, this is basically the elliptical region, less or equal than alpha. This will be the safety region. We have to stay within this region. That probability has to be bigger or equal to P. So defining G of theta as before, B as before, this will be the distributional formulation. This formulation will be equivalent to a univariate quantile formulation. So in this univariate quantile formulation, we only basically look at the quantiles of the chi-square distribution. And of course, this can be generalized to many other dimensions when the problem is that problem of elliptical safety regions. Now, what about linear safety regions? In example 3, it said the following: major consideration when conducting medical surgery with a robot arm is the risk of hemorrhaging a vein, artery, or even capillaries. Capillaries are of particular concern when you're talking about brain surgery. When the probe targets a point mu, random vibrations cause the actual point of incision to be a random vector that has mean mu, but it's a random vector. So in example 3, near the point of incision, blood vessels often look like straight lines. So the risk mitigation will be to constrain the probe to avoid regions where the risk of hemorrhaging exceeds a certain threshold. So here we imagine that a doctor, so in this particular example, a doctor has specified a point of incision on a patient for the robot arm to probe. That would be the point mu, that's the target point mu. She has specified a line at the boundary of a blood vessel near the target mu. So the objective function aims to minimize the distance between the current position of the probe and that target. In other words, we want to minimize this distance from the target. So we want to minimize J of mu, subject to linear constraint. So this will be the linear safety boundary. The problem here, the probability constraint is equivalent to a quantile constraint. You can look at the paper to see how we prove it. It's basically using the fact that we have normally distributed random variables, and we're using the fact that normally the sum of normally distributed, or in this case difference, random variables is also normal. So we do transformations to rewrite the problem in terms of random variables that are independent of the control variable, which in this case we call mu, and which are univariate. So again, we can use the formulation and the theorems that we proved in the first part of the paper. And so these are complex functions, and we can use all the gradient-based methods. These are our experimental results using certain values. And we can see here that the algorithm, as usually, tries to target the unconstrained optimum. So the algorithm is trying to go in this direction towards the unconstrained optimum. But because the Arrow-Hurwitz algorithm is uses the constraint, then it basically bounces back and forth until it finds the optimal solution. The optimal solution, I would like to point out that in this optimal solution, it's interesting to see that we are using the criterion that we want to remain within the safety region with probability at least 0.95. Now, if we were only to look at the 95, quantile, in 2 dimensions, that 95, area is this particular circle. And so a conservative solution would have been to look for a point theta, a point mu here, a little bit farther away, so that its curves, its level curves would touch, just kiss the boundary of that line. But we would like to point out that that naive solution, which would only want to look at the point where the 95 area in the two-dimensional distribution touches the line, is more conservative. So we do better with this formulation because we actually get closer to the point where we want to hit. These are the concluding remarks. We know that quantile ideas are not new, of course. The constraint, as it was stated from the beginning, can also be written in terms of the random variable zeta, which is g of theta and xi. Now, this was done in, this was done in an interesting paper, a paper in 2020, where they're solving chance constraint problems via a smooth sample-based nonlinear approximation. And I found this paper fascinating because they really use a lot of dimensions. And I really liked, this picture is taken from that paper, and I really like the way that they visualized it. Basically here, they're saying if we take the distributional formulation, then the constraint looks like this, the pointed black line. So that will be how the constraint looks like with the distributional formulation. And everybody knows that if you use a gradient-based algorithm, it's going to be slower as it gets closer to this seemingly flat area. The quantile formulation is the red line, and the red line is a lot steeper. So it's the convexity of the red line is, well, the curvature is a lot more pronounced. And so it accelerates the algorithm quite a lot. I hadn't really thought about this until I saw this paper, but I thought that this was really very nice. Now, what are they doing, which is different than we are doing? They're doing numerical. They're doing directly with the variable zeta of theta. So now the quantiles depend on theta. So one has to use estimation techniques, data analysis, a lot of statistics in order to be able to pull this through. What we have done is mostly theoretical. So it's the theoretical foundations and the basis for understanding why the quantile formulation is so much better, so much more efficient. It's interesting that there is another reference where they are using evolutionary algorithms for many, many dimensions. Again, this is, of course, what we're seeing nowadays, a lot more problems where the dimensions are really unwieldy, in the thousands and sometimes even millions. and they're trying to search for solutions using evolutionary algorithms. So quantile formulations quantile ideas are not new. So what are our contributions that are original? We have identified the vanishing gradient pathology for general probability constraints in the distributional formulation. And we believe that that is really the main reason why many numerical algorithms have difficulty with handling probability constraints. So we have identified that theoretically. We've given a proof of divergence of gradient-based numerical methods due to the vanishing gradient of the distributions. And furthermore, we have identified what are the sufficient conditions on the safety region function under which the problem can be reformulated in terms of the quantile of the distribution F. So those are the contributions of this particular paper. But there's a lot of work that can still be done to extend this, these results. The condition of the monotonicity of J can be weakened, and we're working currently on those ideas. When F is not known, the distribution of the underlying random variable or vector Xi, the idea would be to use F of theta as the distribution of the zeta random variable, like in the papers that I just mentioned. And so that would be derived from data, or even data driven, in case that it's a streaming data. Now the quantiles will depend on theta. And the main challenge is that because we're using gradient-based algorithm, how do we estimate the gradient of the quantiles in a consistent way that we can insert them in what we call a stochastic approximation and prove convergence? This is something that we're currently working at. It's one of the extensions. The other extension that we would like to pursue is what happens when we have many dimensions for the quantiles. In the work that we presented, we had multivariate problems, but in those multivariate problems, clever transformations transform those problems into one-dimensional distribution function. What we think now is that we could work directly with multivariate random variables, try to explore defining an appropriate ordering for multivariate problems and multiple constraints, an extension of the quantile formulation using constraint-based orderings. So those are extensions of the work that we have, and that is about the end of the presentation. Thank you very much for your attention. And now we will pass to the questions. Thank you.